Contrarily to Nikos, I choose not to present something which is the state of the art now, but to take another approach, which is the retrospective one, and to start with a historical way of how the demons were introduced in medical image registration and how they evolved up to state-of-the-art method still working right now. So this is more or less the map of the talk with the work of different PhD students over time. And I'd like to start with the deformation registration landscape in medical imaging in the 90s. And so in computer vision, there were quite a few methods around optical flow. So optical flow is basically you assume that between two consecutive steps, the intensity is conserved. So you can differentiate the sum of square difference. And then you get a displacement. And you have many choices because you have one constraint only, the conservation of intensity for 3 parameters in 3D, the x, y, z displacements. But if you normalize that, if you take the pseudo-inverse in your system, then you have a unique solution which is called the optical flow. So it's basically based on the conservation of the intensity. Now in medical images, there was quite a few work on linear elastic deformation. And the first one is Brois in 81, but it's mostly popularized by Rusena Baxi and later by Jim G, who did it for, who implemented that for 3D images in the early 90s. And then one of the big problems was that if you take something which is elastic, like the C experiment that we saw in Nikos' talk, if you take a very small thing and you want to stretch it to something which is very large, so in one word, if you want to obtain very large deformations, elasticity is not sufficient. And basically, you know that when you're pulling on an elastic, you can, there's always something pushing you back. So you can never reach exactly how far you would like to go for very large deformation. So Gary Christensen introduced the fluid registration. And one of the ideas that you can flow the image and have a deformation which is still diffeomorphic. And so that's basically the global setup. Now if we enter a little bit into the math, so I will try to be simple and don't look too much at the equations. The idea is really to understand what's behind. But just for the notation of this talk, we're going to represent the deformations by a displacement field. So it's basically this vector field U here. And then we're going to consider, to start with, that the similarity measure is just the sum of square difference. So it's a simple one, but we could use normalized cross-correlation or other mutual information like criterion. And then the idea at that time was to take the gradient of that, and since we want to put it in a mechanical system, we're going to consider that the gradient of that similarity is a force. So in our case, we get the force, which is just the gradient of this. And now we want to compute how the body system is moving under this force. So if we take an elastic material, then the differential of the elastic energy is just this, and we have the equilibrium if we solve this equation. So you can see here that it's written like big mathematical equation, but if you take your displacement vector and you put it at each voxel, and you put it in a big vector, so you have U as a big vector, these are linear operators. And so basically what we have here is a linear system which has the size of the image times 3 because we have 3 components. So it's basically this is a linear system that we have to solve. Just imagine that you're doing finite difference for the differentials. This is written as a linear system. Now the matrix is very big. Okay? So now if we take a viscous fluid, we have exactly the same equation, but not on the displacement, we have it on the speed. So we first have to solve this system, and then we integrate again to get from the speed to the displacement. So we have 2 times to integrate. So that is the way registration was done at this time. And it was, well, working. But, I mean, imagine in the 90s, maybe some of you were not doing computer science, but we didn't have the PC like that. I mean, the personal computer was not exactly the same power. So these differential equations, they were very costly to solve. And when I say very high computation time for solving the Navier-Stokes equation, Gary Christensen was spending half a day or so on a massive parallel machine, one of the most powerful computing machine at that time. So if we want to have that as a real time, that was not really working. So here is where Jean-Philippe Thirion came with the idea of the demons. And contrarily to this illustration, it's not a devil, but it's a demon. And the definition is, I mean, if we take the dictionary, it's some kind of semi-god who's controlling some part of the world. And that's a good definition for what we're going to do. We can see it also as the personification of a force. And that's exactly the idea that Jean-Philippe Thirion took. And actually, the name is coming not from, from this definition, but from Maxwell's demons, where actually, if you know the experiment of Maxwell, the idea is that you have a container with 2 types of molecules, and then you put a semi-permeable membrane here, and you put some small demons. And they're just stopping molecule A from going from one side to the other, and stopping molecule B from going the other way. They're doing nothing, they're not consuming energy. And at the end, because you're just stopping the molecules to move from one side to the other, you will end up with a completely separated, you're separating the 2 types of molecules. So this is a paradox for thermodynamics. Of course, the thing is that you're not consuming energy to actually, in terms of speed of the particles, but you're consuming energy to detect is it molecule A or B. And if you take that into account, you're not breaking the second law of thermodynamics. So the idea of Jean-Philippe Thirion was to do something similar. You put small demons everywhere in the image, and they just look at the intensity where they sit and the intensity at the current place of the other image. So you just look, locally, so meaning that you can take the intensity and the gradient. And depending on how the gradient, if the intensity in the other image is higher, you push along the gradient of your image in one sense, and if it's lower, you push in the other sense, in the other way. That's it. That's the idea behind the demons. And if you take this type of images, this is the forces that are created, and then you integrate things. So the idea is you have demons all over, they push independently, and then you have a second step where you mix everything together to have a global displacement. And this is what is the registration between the 2 images that were obtained. So the exact algorithm that was proposed, and it's just an algorithm, there's no justification, is we start with the identity, then we take a correction field, which is, here we recognize the difference, the error, and this is basically the gradient of the similarity criterion. This is divided by some kind of strange thing, normalization, which is actually the key to one of the key to the success. Then we regularize that, and we can regularize it in 2 ways. Either an elastic regularization, which is basically that we take the correspondences. So how is it? We compose the corrections with the displacement field. So that is the composition of the 2 fields. So we have the current deformation. We update it with the correction field. We obtain a new correction that we now filter with the Gaussian, and that is our new displacement field. So this is an elastic-like deformation, because if you remove the forces, then you will iteratively smooth the deformation, and that will go back to identity gradually. Now, if we do it slightly differently, we take the correction field and we just smooth it. This is basically like smoothing the speed vector field, and then we can compose, and this is more like a fluid approach. So the idea in this algorithm is that we can mix elastic and fluid, and it seems to work quite well. And this is actually one of the examples that Jean-Philippe Thirion originally presented. So I think it's dating from 95, 96. So this is the deformation of an atlas which was provided by Ron Kikenis from Brigham and Women's Hospital to an image, and we could deform the image and then transport the atlas and then label the image. Okay, so just by the way, this type of methods was also used by Alexandre Guimond very quickly after to build templates of images, and this was the basis, just to keep credit, to give credit to the people. This was the basis of the implementation of the demons in VTK early, before actually ITK was existing, and it was later used to build the ITK version of the demons. Okay, so now we have an algorithm, and the status is the following: it's fast, it's efficient. So I should say that I probably did not mention, but where Gary Christensen was taking a few hours on a massive parallel machine, Jean-Philippe Thirion was basically arriving to register images in something like 15 minutes on the standard PC, which was much better from a computational point of view. However, there are big cons. There are not only, I mean, fast is good, but why is it working? So that's one of a good question. Why is that working? When will this algorithm fail? How can we change the similarity measure? Because so far it seems to be based on the sum of square differences. So this question drove us, or actually Pascal, to think a bit more and to try to explain what could be behind this algorithm. And the idea, so there were several tries to do that. So first, what you saw before for the energy that we're registering is this term and this term, the regularization. So we tried to play changing the terms to try to explain the two steps of the demons, but that was not working so well. So the best explanation was this one, actually. It's basically, we consider that we have the similarity measure, which is on one type of displacement, which would be what we call the correspondence between voxels. And then what we want is to have a regular transformation. So we are distinguishing two things now, transformation and correspondences. And if you imagine what it is, you're deforming an image, so you have an image that you flow. Now if you take a real voxel, when you're deforming the voxel as a point object, it's not exactly, I mean, it's actually the integral over what is inside the voxel, so there might be some kind of uncertainty. And even if you take different subjects, we are trying to have a deformation that fits one image onto the other, but there might be errors. Actually, the exact correspondences might not be exactly what is in the transformation. So one of the ideas is to add something in between, which is to say we want to optimize the correspondences, exactly as Nikos showed with the useless registration at the end. But we want in the meantime to have a transformation which is very smooth and which is very close to the correspondences. So the introduction of this correspondences as an auxiliary variable is one of the key that is making things much simpler. So by the way, this idea of introducing auxiliary variables, it's also used in many methods in computer vision. So the split Bregman method is exactly this type of trick. So it's a usual trick, but it simplifies a lot of things. And in particular, here what's happening is that if we take this criterion, So here the idea is we have the correspondences. You remember the correspondences are between points. They are independent. I mean, there's nothing about spatial correlation, and the transformation should be smooth. So now if we want to optimize this criterion, we have two variables, and we can make an optimization alternatively over one and the other of the variables. So if we optimize over C, you see that we basically just have to optimize this part of the criterion. And now we don't have to care really about the regularization. It's just a least square here. So we are going to end up with a much simpler criterion to solve, which is almost a least square. And we can use, we're going to see that just in 1 minute. We can use gradient descent. Well, the first order gradient descent, which is not very efficient. We can go to Gauss-Newton or pseudo optimization method, and that is one of the second key to explain the Demons algorithm. Now, the second part will be the optimization with respect to the second variable, the transformation, and we can see that we have to solve this criterion here. And here, one of the key idea of which is behind is if you take here the norm of the gradient of the displacement field or the curvature tensor, the second order derivative, you will end up with a linear system to solve, exactly as we had before for solving the fluid flow, right? So we are not gaining anything. So here, one of the ideas that if we take some specific type of regularization, which is actually a quadratic energy, then we can have a closed form solution using a convolution. And convolution can be implemented efficiently, so we can have a closed form solution for the regularization. And here is basically the optimization interest of the demons. So if we just take the first part, the correspondences, so we want to optimize this criterion with respect to the correspondences. So one of the ideas to say, okay, if we want to have something efficient, we want to approximate this criterion by a least square. I mean, if we're taking the gradient, that's the first order. I mean, if we're taking a Taylor expansion of the criterion, the first order will be the gradient. The second order will be the Hessian, but the Hessian matrix will be very large. So what we can do instead is to take this criterion here. This is the error at each point, and we're going to do a first order Taylor expansion, right? So this is basically how we can write things. So this is the error between the two intensities. Then we have the gradient, which is related to the displacement that we're looking at, okay? Now, if we put this approximation into this criterion, the criterion can be rewritten that way. And now if we optimize around the correspondences, which is close to the transformation, this term is 0. And we end up with this equation to solve. And if we gather all the terms together, this is the system that we have to solve. So you will tell me, but we are in the same situation as for the fluid flow of Garrett-Christensen. We have a linear system to solve, and this U here is the size of the image once again. Yes, but this is not a random linear system. This is actually a system which is very simple, because here we have a closed form solution for this inversion, because it's a scalar equation, and the closed form solution is this one. And here you recognize that we have, with respect to the, we are very close to the Demons forces that were proposed before. If we take a local estimation of the image intensity variance, which is just basically we take the error at the point where we are. This is the error in intensity, and we're going to pretend that this is our variance on the image error. And then in that case, the second sigma here, you remember that sigma I is the error that we're allowing on the intensity. Sigma x is the error that we're allowing between the transformation and the correspondences. So it's basically the size of a voxel. I mean, if we have a voxel which is the center of a voxel which is matched to, or which is deformed to within another voxel. That's basically the best we can do for the correspondences. So we can take sigma x, which is of the order 1, and then we end up with this formula, which is exactly what Jean-Philippe Thirion proposed. So here we have an explanation of why is it working, and this normalization here is coming from the Gauss-Newton scheme, which is basically an approximation of the second order derivative of the criterion. And this is one of the key things, that this normalization that makes things working. So one more observation. It was working a bit too well, so we were trying to put some weights here to make things better or smoother, actually to use exactly this formula with different sigma I and sigma x, and it was not working as well. It was, I mean, going crazy sometimes, so it was a bit difficult to understand, but actually the idea is that if we take this formula here, because here we have this square and we can extend it and this is always positive, we can show that actually the norm of u here is always less than 1/2. What does it mean? We are working in voxel size here, in voxel units. It means that each of the displacement of the corner of the voxels is not reaching the center. It means that the two arrows cannot cross. We can't have a folding at each step. This means that the update field that we're computing that way is diffeomorphic by nature with trilinear interpolation. And that is something which was unexpected, which is just the result of the formula, and this is one of the things that is actually making the algorithm working correctly. It's each time the update is diffeomorphic. So it means that at each step, we do not fold the image in any case. Okay, now the second part of the optimization is the regularization. And what I told you is, instead of taking just the norm of the gradients of the displacement field or second order derivative, we're going to choose something more complex. And we're going to choose a formula which is R4, so you don't have to read it or to. The idea is just that instead of taking just the first order or the second order, because we have matrix which will be, when we discretize things, we're going to end up with matrix which will be sparse. We're going to go to infinite order. We're going to penalize every differential at any order up to the infinity. So we're going to choose something which is like that, and there is a specific reason why we choose that. It's because if we minimize this criterion with this regularization, there is a closed form solution, and the closed form solution is the convolution with a Gaussian. And we all know that the convolution with a Gaussian is very efficient. So we have a closed form solution for this step. So here the trick is the following. Instead of really controlling what is we are never computing actually the norm of the regularization. We are just computing, we are putting things in a way we can solve it efficiently. So instead of trying to have matrices which are sparse to be simple to invert, we're going to a full matrix, but we know the inverse. We know how to compute the inverse so that it is efficient from a computational point of view. So if we extend this idea to vector fields, so if we look actually for all the quadratic filters that are separable, so if you take that for a scalar image, there is just the Gaussian, which is separable and quadratic. But if we go to vector fields, there is a family, and this family is parameterized by kappa here. And this kappa is somehow encoding more or less the compressibility of the material which is behind. So we have something that can also be more general. And here is the reference on the filter that realized that. So here the key idea is with respect to many registration algorithms where the regularization criterion is very simple and it's taking the lowest order that we can on the transformation so that the system is easy to solve. Here we take a big system which is a matrix which is very wide, but we know the inverse. So we can complexify the thing. Originally, I said we could either smooth the correction field or the transformation itself, and we obtain either a fluid or an elastic-like regularization. So we can do the same thing here if we add something which is here related to the difference between two transformations. So it's actually the velocity and the regularization on the transformation. This would be the elastic part, this would be the fluid part. And we can still show that we can obtain a result by convolution. And this is given by this formula. But anyway, it's not important. The important thing is that we still obtain the result by a convolution. So it's still, we are maintaining the efficiency, and we can have a mix between elastic and fluid regularization. Okay, so this is the summary of the framework. We have actually, if we want to go fluid, we have the similarity energy, the regularization on the transformation, a regularization on the evolution of the transformation, on the speed of the transformation, and here a term which is binding the correspondences and the transformation. Okay, that's the key thing for explaining the Demons algorithm. Now, if we want to go to add some information to our image. So, for instance, we could, on the brain image, we could extract the sulci, and we could want to match the sulci to the sulci. So it's kind of a feature-based approach where we want to add things. Well, in this criterion that we had, we can add a new correspondence field, which will be the correspondences between the lines, the sulci on the brain. Or if you had points, you can have the second correspondence field with correspondences between points. And now the new criterion is the same as before. This is the similarity with the correspondences between image. We want to have the image correspondences which are close to the transformation. And we want to have also the feature correspondences which are close to the transformation. And now we want the transformation to be regular. And here, once again, there is an explicit solution for the transformation, which will be a combination between a convolution for the dense correspondences and splines for the sparse correspondences between features. And this is working quite well for the case of sulci. So this is a section, well, we can see the central and post-central sulci, and this is after registration by intensity. And if we take into account the sulci correspondences, we can see that, we're getting a much better alignment of the sulci, although we have exactly the same error on the images themselves. So here is a solution also to add extra information, anatomical information that we can have about the model. Okay, so now I'm going to go to another step, which was done by, which was the work of Radu Stefanescu. And the idea was that if we go, when we use the demons, it's basically the same regularization everywhere. So it means that we can't adapt regularization to the different types of tissues. For instance, in the brain, we'd like to have the gray and white matter, which are more elastic, and the CSF, which is fluid. Well, that's a fluid, so we expect it to act as a fluid. The second observation is that if you have, for instance, a tumor in the brain, well, you know that when you're registering an atlas to a patient with a tumor, there is no correspondence for the tumor. So in some places, we might have good correspondences. At other places, the correspondences might be completely wrong. And we would like to be able to also weight how much correspondences are faithful or not. So one idea to do that is to revisit the same criterion. So this is the same criterion as before, but to revisit the regularization. So here, remember, we have in all this energy-based, we are weighting by some factor here. And this factor, instead of putting it outside, we put it inside of the integral. And now we make it space varying. So this means that here, if I'm putting a high lambda at some point, I will penalize a lot all the deformations at that point. Now, if I want to have large deformation at one point, I can put a lower lambda at this point, and the deformation are less penalized. Now, the price we have to pay to do that is that we don't have anymore a closed form solution for the second step. So here, the trick of doing the regularization or of putting all the derivatives so that we know the solution, it doesn't work anymore. So here we have to come back to solving linear systems to be able to regularize, and that's why here I'm using the norm of the gradient of the displacement field, because it's actually sparse matrix. And one of the key things is we can work out, and that's what Stefanescu did, work out some parallel method to optimize these equations. So just one of the idea that is behind is the idea to have non-stationary elastic regularization. It's basically coming from diffusion and nonlinear diffusion. So if you take just D equal identity, you have linear diffusion, and it's corresponding more or less to a Gaussian smoothing. It's basically the propagation of heat in a vector space, and that's basically Gaussian smoothing. Now, if we put an operator here which is nonlinear, then we end up with nonlinear diffusion, and that is able to encode different stiffness in the material. So typically, here we can do a rough segmentation and put a stiffness, so which a D here which is very high in the gray and white matter, and we're going to put very low value in CSF and outside, so that it means that we're going to have very high deformation within CSF and much lower deformation, much more constrained deformation within gray and white matter. The second thing is on the speeds itself, we can try to have something which is also non-stationary, and it's basically encoding the information we have in the image. And here you can see that we have basically the gradient of the image, and we know that when we're registering images, the only place where we have information is where there is a gradient. So what we'd like to do when we compute our correspondence field is to basically say, if I have a displacement or correspondences which are given at edges, I want to trust them. Now, if I have correspondences which are given in two homogeneous area, I mean, they can be very uncertain, because if you move the two, I mean, even if the intensity is very close, it will be very close if you move a little bit around. So one of the ideas that if we use this type of equation, nonlinear equation, but stressing the fact that we want to trust the information at edges, then we might be able to extrapolate the information where we have, or the displacement where we have no information. Okay, I'm going to switch the parallelization. I just want to show you a few results. So this is the registration of two images. So one has a stereotactic frame, so you can see the frame here. And this is the affine alignment. So you can see that with an affine alignment, basically we have the shape of the head, but there are a lot of remaining differences between the two images. So here we're just fusing the intensity of the two images, okay, going back and forth from the intensity of one image to the other after registration. And here's the results when the computer will, okay, here's the result of the fluid registration. So you can say this is almost perfect from the image point of view. But exactly as Nikos showed it, if you look at the deformation which is behind, this is actually a nonsense deformation. It's like taking one pixel here to put it here and another pixel here to put it here. And this is actually what's happening. If you take a fluid deformation, each step is diffeomorphic, but if you flow for a long time, for long enough, then you can reach non-diffeomorphic deformation in the end at an infinite time, but that is also depending on your implementation. So in practice, fluid is not enough, but if we do something which is in between, a little bit of elasticity and a little bit of fluid deformation, then this is the result of the deformation. And now we see that in some areas here, for instance, there are differences. And the differences are normal. Some people have 2 gyri at some point and others have 3. Should we match them? Should we force the deformation to have exact correspondences, or should we have a smooth deformation and say, okay, the correspondences might be different from the underlying deformation? That's exactly what the demons is allowing you to do, because we have these two fields, the correspondences and the deformation. And we can make the difference between what is the smooth deformation and what would be the correspondences that you want to see in the image. But now if you see the deformation and if we deform some labels, they will still resemble something reasonable. Okay, so last example is if you have a tumor here. So this is an image with a resection, a tumor resection. And actually the tumor has to be treated by radiotherapy. So we want to warp an atlas to this image. But if we do it without taking into account the resection, then the algorithm will try to fill the resection with some brain. So what we're doing is saying, okay, what is white here is high confidence, what is gray is middle confidence. That's basically, there's not much information. And here we don't want to trust information at all. And if we do that, then this is the original superimposition of the deformed image to the atlas, and this is after registration. And here you see that the tumor is correctly preserved. And if we don't actually account for the fact that the correspondences should not be trusted in this area, this is what we would have obtained, which is the image is completely deformed to fill the resection. Okay, let's now go to the second big step in the history of demons, which is diffeomorphic demons. So we talked together before about optimization methods, saying we're going to optimize a velocity field, and actually I told you each step is diffeomorphic. Well, it was with linear interpolation, but if we want to go farther away, I mean, if we want to change a little bit this formula, then it's not diffeomorphic anymore. So one of the ideas to preserve diffeomorphic is to go into a bit more mathematical structure and to consider that deformation, they belong to a group. So what's a group? It's basically something where you have an identity, and that's no deformation. That's the identity transformation. Now, if you take one space deformation, you take your object, you apply the space deformation. If you apply another space deformation, it means that simply that there is a composition of the deformation which corresponds to this action. So it means that you can compose deformation and you can go back the other way, so you have an inverse. So that's basically what is a transformation group. Now, we often consider that it's smooth, so that it's a Lie group. So example are rigid body transformation, affine transformation, diffeomorphisms. So diffeomorphisms will be transformation that are invertible, and we can differentiate, and we're going to say that up to infinity. So they're really smooth deformation so that they cannot fold. There cannot be any folding. So why we're interested into diffeomorphic deformation? Well, if you try very large deformation, and if you don't impose that it is diffeomorphic, you will find foldings. The problem is that you will find foldings at every point. The foldings will appear they appear much more easily than the correct deformation themselves. So the idea by going to diffeomorphic registration is not that this is the ultimate model. It's just that because preventing the image to fold is much better than folding where you don't want it to fold. Okay? So it's a mathematical model. But the key question is how to guarantee that we are not folding. So, okay, so that's the natural operation we have in groups. We want to be able to compose deformation. And if all the equations that I wrote before were gradient descent. So gradient descent is basically we are adding something to a current deformation. And implicitly what I was doing is adding something to the displacement field. Okay, but if I'm adding things to a displacement field, then I'm going to end up with something which is not a deformation. I mean, I can have folding. This is not a natural operation in a transformation group. This is a natural operation. So the key thing is we should not add, we should compose. And this is the idea which is used in LDDMM, large diffeomorphic metric mapping methods. So this is a big slide. We're going to see it tomorrow. So it's just a flash. What I want you to remember just now is that in LDDMM, the deformation is encoded by a series of velocity fields that you compose the motion of all these velocity fields to obtain the final displacement. So the idea is you have a time-varying velocity field, and by integrating the flow, you obtain a diffeomorphism. Okay? And the other thing is we have a distance, which is the norm of this velocity field. But we're going to come back to that tomorrow a bit more. So I'm going to skip that. One of the ideas that we exploited, or Vincent Arsigny proposed at MICAI a few years ago, was to say, well, why using time-varying velocity field? Why not using stationary velocity field? So not varying in time. So this is the idea. You take here two velocity fields, we merge them, we add them. So velocity field is it's a vector space, so we can add velocities, subtract velocities, okay? So here it's basically a rotation in one direction, a rotation in another direction. And now instead of considering that these are displacements, we are going to consider that these are velocities. And what we want is to flow along the lines of this vector field. And if we solve the flow, then we find that this is the deformation. And the deformation is diffeomorphic. So this is one of the ideas that was used for the what is called the stationary velocity field framework, and we're going to use it a lot in the following. And the key step here, why is it interesting to use these stationary velocity fields? Because there are matrix equivalent with very efficient algorithm to compute. So the flow of a stationary velocity field here, this would be the group, what we call the group exponential. And if you take matrix group, you know that there is a matrix exponential. And the matrix exponential has some property, and the property is that the exponential of a matrix, you can just take the matrix divided by 2 and compose with the 2 exponential. So if you take x of u over 2 times u over 2, it's going to split into x of u over 2 composed with x of u over 2. And there are efficient algorithms. And here the idea is the same. If we want to compute the flow of this point along the velocity field, we can just say that this is the flow for half a time composed with the flow with half the time. So the flow of time 1 is the composition of the flow for half the time with itself. And now we can use that recursively, meaning that instead of having n time steps to integrate this equation, we're going to have log n time steps for the same, for computing the same thing. And that's the idea. So if we have a velocity field, we're dividing it by a number of steps, which is a power of 2, which is sufficient so that it's very small. Now, if it's very small, if the velocity is very small, then we can interpret it as a displacement. Okay, so we can interpolate the displacement in the voxels, and we have, this is basically the identification with a very small time step. We're saying the velocity field is actually a displacement field. But after that, instead of just scaling up the displacement field, we're going to recompose by composing the deformations. And we're going to end up with the deformation, the flow of the final deformation. So we have an efficient way of computing the exponential of a stationary velocity field, the flow of a stationary velocity field. And the idea of Tom Vercauteren was to say, when we're doing the demons, we're computing a gradient somehow at each time steps, and then the composition should be done carefully. So we have a correction field, which we can interpret as a velocity field. And instead of saying here, I am at this current deformation, I want to go in that direction. This is my correction field. So instead of adding, in which case you see that I'm leaving my manifold, I'm going to compose and take the exponential, which is basically take the geodesic on the space and compose. And so this is the idea. The update is written now like that. Instead of phi of x plus something, we're going to use compose with phi of f, compose with the exponential. And now whatever correction field we have, we know that this is always a diffeomorphism, and thus the composition will hopefully be a diffeomorphism. And I'm saying hopefully because in theory, this is a diffeomorphism, but in practice, we are implementing that on a grid. And this discretization in a grid is not guaranteeing the fact that we have a diffeomorphism. So some people try the diffeomorphic demons and say, but the result is not diffeomorphic. I mean, if you follow the path that is optimized, this is always diffeomorphic, but if you summarize the final deformation in a displacement field, that displacement field might not be sufficient to encode the very large deformation that you have. Okay, so I'm going to just skip that to go to a few extensions, more recent extensions on the demons, and finish with the log demons, which is the algorithm that I will detail more tomorrow. So the first extension for cardiac images was to actually realize that if in the cardiac contraction, when the muscle contracts, it's almost an incompressible deformation. And one of the ideas is, well, if we can restrain the deformation that we're computing to incompressible, that should help a lot in finding the deformation. So that's also something that Julia made a long time ago, in the 15 years ago, something like that, 2001 or 2, if I remember well, with B-Splines. So here in the demons, the idea is that if we have a velocity field, well, we can just impose the divergence of this velocity field to be 0, and then automatically the flow of that field will be an incompressible deformation. So the idea is in the demons, instead of considering all the corrections that the correction field that we can have, we can just project that on the space of divergence-free velocity fields. And that is done with actually solving this equation, which can be done relatively efficiently. So we can remove the divergent part of the velocity field, and we end up with a correction which is always volume preserving. And we can now compose that with the current deformation and update the deformation. And here's an example on the typical image we have for the heart. So it's a cine MR image. So here it's a section. You see the left ventricle, the right ventricle, and here it's more or less vertical on this axis. And you see that we have very thick slices. So it's not so evident to have a very good measurement of the motion from these images, but this is the standard images that we are dealing with. And here is the strain that we're estimating from the deformation and compared with the strain which is deformed, which is computed with echo directly, but the problem is that we cannot really validate because echo is 2D and here we're computing something in 3D. But anyway, the only thing is that if we add incompressibility, so if we add some prior about what we expect our deformation to be, some anatomical prior, then the results are better. Now, if you impose a prior which is wrong, then it's not going to work either. So you should be very careful about your prior. A second, still for cardiac images, a second improvement that can be done is to say if I have two sequences, so assume that this is patient 1 and patient 2, and I have time sequences. So here I have deformation over time. I can actually correct for all this deformation and build a pile of images over time. And here for the second patient, I'm going to have a pile of images. And to register the two patients together, we can think that using all the time frames would be a better idea. So we can do that, and this is what is instead of having each image which has one channel, one intensity, we can have multi-channel images, and we can register that together. So one of the things in the demons is that we can do exactly the same Taylor expansion that we did before. The only thing is that here in this equation, before we had a scalar equation. We had only one. When we had one intensity, we have the inversion lemma that allows us to find a closed form solution. Here, in that case, we have a matrix solution, and we have to invert the matrix. So it's not a big matrix, which is the size of the image, but it's still a matrix to invert. So it's more expensive, and we have actually to solve something. At each point, we have a linear system to solve. And this is the same thing that is at work if we want to register DTI images. So you might know or not know that diffusion tensor imaging is actually an image where at each point you have an ellipsoid, which is representing the currents matrix of the motion of the water, the Brownian motion. And what we want is to register, if we have different subjects, we'd like to register these two images. Now what's happening is when you deform an image, you might locally rotate things, and you need to reorient the tensor. So it's not just taking the components and resampling the images. There is something else, which is the tensor reorientation. And Daniel Alexander first showed that if you do that with just the standard affine action, it doesn't work properly because it doesn't preserve the eigenvalues. And the eigenvalues, these are physical values because it's diffusion. And so we had to use different strategies to reorient, and that is some kind of a transport of the tensor. We have to define a proper transport of the tensor by the deformation. And there are two main methods: finite strain and preservation of the principal direction, which are usually used. So I personally prefer this one because there is a formula which is easier to write. This one is basically more an algorithm, but it can still be differentiated. And if we use that, then we can include that in the demons once again. So I won't really go into detail. There is a closed form solution for the pose estimation, so that we can write the system in the different equations. And now we can apply that to different images. And here, if you look at the target image, if we approximate the gradient without reorienting at each step, this is the results that we find. And if we really compute the exact gradient with the reorientation of the tensor, then it's working much more properly. So this is just to show that quite a lot of things can be embedded in the demons framework. Now I just want to finish with one idea, which is related to LDDMM, and it's just setting the ground for part of my talk tomorrow. I said that LDDMM is basically parameterizing the diffeomorphism with time-varying velocity fields, right? And then the idea of Vincent Arsigny was to say, well, we may actually use stationary velocity field because it's much simpler to compute. But what we did in the diffeomorphic demon with Tom Vercauteren is basically to take the current deformation and compose it with the flow of a stationary velocity field. It's not we are still encoding the deformation by the displacement field. So now the idea of the log demons is that we can directly parameterize the full diffeo by the flow of a stationary velocity field. So this is requiring one more step. So this is this idea that we can parameterize the deformation by its logarithm. Basically, in the matrix group, it would basically consist of parameterizing a matrix with its logarithm, and then we take the exponential to get the deformation. It's working only if we know how to update the parameters of the deformation. And one of the key things is in the demons, in the diffeomorphic demons, we have not x of v here, we have a deformation which is encoded with a displacement field, and we're composing with the exponential of a small update, right? If we want to stay in the log of the deformations, we have to know what is the stationary velocity field, which is the result of this composition. And there is a formula which gives that in normal Lie groups, which is called the Baker-Campbell-Hausdorff formula, which was proposed by Matthias Bossa a few years ago. And this is an approximation, but it's working very well for optimization. Remember that at each step we're optimizing. So if we don't have the exact solution to this composition, we might correct it at the next step. So it's not really a big problem. So now if we reformulate the Demons criterion with this type of formula, so this is the similarity criterion, this is the deformation here, this is the link between the correspondences, so this is the correspondences, sorry, the deformation that correspond to the deformation, to the correspondences. Here, this is the link between the transformation itself and the correspondences. And now the regularization. We can have exactly the same setup as before, where given two images, we compute the Demons forces, so we can compute them forward and backward. Then we can compute the update with the Baker-Campbell-Hausdorff, and we can combine the forward and backward deformations. And then we regularize the stationary velocity field with a Gaussian. And that is the heart of the log Demons algorithm that now we can expand with other types of similarity criterion. So for instance, the local correlation coefficient, which is a variation of the normalized cross-correlation. So we can show that it's working quite well. So here are just to finish, two MRI images. And we add a multiplicative bias and an additive bias. So this is typical of what we observe in MRI images. And if you do the sum of square differences, this is the deformation, the Jacobian of the deformation that we observe. And you see that it's basically, not very good. And if we use the local correlation, it is much smoother, and it is corresponding to something which is more anatomical, and it is invariant with respect to additive and multiplicative biases. So we can update now the diffeomorphic demons, and we can show that they're reaching, almost top-level performances on different databases. So I just want to finish with a very small summary of the zoo of the deformation of the Demons registration algorithm that we saw. And just one interesting thing is that there are many implementations which are available. So of course there are implementation in ITK. There's the implementation of the diffeomorphic demons. But for the log demons, almost all the versions that were developed are available online. So the version of Tom Vercauteren is available there. There is a new version by Hervé Lombard, which is MATLAB. The LCC log daemons is also available. The tensor log daemons is available. There is also a version where we're doing locally affine embedded into that, whose source code is available. So if you want to try, I mean, you just have to choose which implementation you want to start with. And I finish on that.